This presentation is about the differences we find between Newton's equation for wave speed on a stretched string versus the wave speed on a spring mass chain calculated using Newton's own force balance equations. That is, on one side we have Newton's equation, wave equations that he derived on a stretched string, and on the other hand we have the wave speed that we derive using Newton's force balance equations on a spring mass chain. So ideally we expect that the speed found after calculating the normal mode shapes and frequencies from ab-initio force balance equations should match the wave speed found by Newton using an alternate method. He sort of applied the force equations at a higher level abstraction of the spring. We find Newton's wave equation implies a constant non-dispersing speed, but the ab-initio force balance equations give a dispersing non-constant speed. The error in speed at higher frequencies is over 57%, and the error in frequency estimation at higher frequencies can be as high as infinite percent. Newton's method of analyzing the waves on a string does not really resolve the behavior of individual oscillating elements making up the string. Implicitly, we all imagine these oscillating elements to be present in a vibrating string. We have probably not tested that idea rigorously enough. We shall do it here now. Basically, we can imagine this string tied between two infinitely heavy immovable edge masses or edge walls as a chain of spring mass units. If the original spring has uniform mass distribution and uniform elasticity along its length, then we can assume that it is made up of similar springs, all with same resting length L, same spring constant K, and with same mass units, say of m kg each. That is, all these mass units in violet color have the same mass m. In Newton's analysis, the string is assumed to be stretched. In fact, we will see later that if the spring is not stretched, then it cannot support transverse oscillations. So we assume each spring is pre-stretched by some amount h, and this h is much smaller than L, the resting length. Suppose I is the index number we use to address each mass. The leftmost mass is the first mass, I equals 1, and the next to it is I equals 2. This is some generic ith mass in the middle, and this is the last nth mass. There are total n mass units and n plus 1 springs in this chain. When this system is absolutely at rest without any disturbance, each spring is stretched by h meters. So it has a total length L plus h. L is the resting length plus h is the pre-stretched length to create tension in the spring. Suppose we consider the left edge wall as our reference, 0, along the x-axis. This is the origin of x-axis. Then the first mass is at L plus h distance. The second mass is at 2 times L plus h distance. The ith mass is at I times L plus h distance, and the last mass is at n times L plus h distance. The right edge wall is at n plus 1 times L plus h distance from the left wall. And this is a generic ith spring in the middle, to the left of the ith mass and to the right of the I minus 1th mass. Suppose at a particular time instant, the ith mass is disturbed by xi units along the x-axis and yi units along the y-axis from its rest state shown on top. So this is the resting state, same as this these three masses here below. And this is the disturbed state at some point in time. So after some disturbance, the new x-axis distance of the ith mass is I into L plus H plus xi. So on top, in the resting state, the x-axis distance was just I into L plus H. Now it has got an extra factor. Now the disturbance is I into L plus H plus xi in the disturbed state. So this plus xi is the extra factor. Similarly, for the first mass, x-axis distance is L plus H plus x1. And 2 into L plus H plus x2 for the second mass, and so on. So this ordered pair in red, say xi comma yi, shows only the disturbance values xi, yi. They do not show the absolute xy coordinates. This is the disturbance from mean resting position of these masses. We assume that these disturbances are so small that these differences, the absolute value of xi minus 1, and the absolute value of y subscript I minus y subscript I minus 1, are much smaller than even h. That is, h itself is small in comparison to L, the resting length. But these xy disturbances, the xy disturbance differences, are even smaller than h. In this limit, we can make neat first order linear approximations to force equations and reduce them to simpler forms. So that is why we use these approximations. The left edge of the ith spring is disturbed by x I minus 1, y I minus 1, this ordered pair, perturbation. This perturbation corresponding to the I minus 1th mass, the moment of I minus 1th mass. And the right edge of the ith spring is disturbed by the pair xi, yi. This perturbation corresponds to the ith mass movement. So the length of the ith spring is Li is square root of L plus H plus xi minus 1 whole square plus yi minus 1 whole square. So this is the Euclidean distance of the between the two edges of the ith spring. So this can be approximated. We can make so this approximation below because of these inequalities. So xi minus 1 is much less than h. The y difference is also much less, the y disturbances, and h is also much less than L. So under these conditions we can make, so Li is approximately now L plus H plus xi minus 1 plus yi minus 1 whole square by 2L. Further, as a first order approximation, we can even drop this y disturbance terms, because it has a second degree variation which is relatively insignificant with respect to L plus H. The force exerted by the spring depends on its instantaneous length, rather on the difference between Li and L, which is this factor h plus x minus x subscript I minus 1. So this is the first order approximation of the instantaneous disturbance in the length of the ith spring. So this shows the disturbance, how much the ith spring has been disturbed from its resting state. When we multiply this, the disturbed length, by the spring constant k, we get the force or tension exerted by the ith spring. So using the disturbance length, multiplying it with the spring constant k, we can find the x and y axis force components. For the ith spring, along the x axis, we get the x component f of ix. The ith spring x component f of ix is nearly equal to k into h plus xi minus 1 into cos of some angle. Here, this angle inside the cosine function is the angular displacement of the new spring position with respect to the resting position of that spring. So this angle is close to 0, hence the cosine function will simply be 1, as shown in this step 2 equation. Along the y-axis, we get f of iy, the yth component of the ith spring, the force, is nearly equal to k into h plus xi minus 1 into sine of the same angle that was there in the cosine function above. So this sine function will be close to the ratio of the y-axis disturbances, the difference in the y-axis disturbances, to the resting length of the spring, that is yi minus 1 divided by L, as shown in the fourth equation in the list. So using the approximate forces or spring tensions calculated from the second and the fourth equation in the list, we can find the instantaneous acceleration of each mass. The d square x by dt square and the d square y by dt square terms are the x and y acceleration components of the ith mass. The acceleration of the ith mass is balanced by the tensions of the ith and the I plus 1th springs connected to the mass. So that is this ith mass. On the left side there is spring I, and on the right there is I plus 1th spring. So the net balance produces the acceleration of this ith mass. So this is the ab initio first principle equations, force balance equations. We frame such equations at each of the n mass units. Using this force approximation along the x-axis, we get the x acceleration of the ith mass as this. Here there are force components of the ith spring and the I plus 1th spring. When we expand these terms, we get these simplified equations below. So for a generic mass n, the equation is m d square xn by dt square plus k into xn minus 1 minus k into xn plus 1 minus xn. This equals to 0. So the kh factor that we find in the top, the kh factor from the left spring gets cancelled by the kh factor of the right spring. So we will be left with only these x disturbance differences. So the kh factor disappears, only this xn minus 1, these differences, these x-axis disturbance differences, they remain in the force balance equation. So note, this equation does not have any term with the pre-stretched length factor h. The longitudinal normal modes do not need the background tension in the spring for its existence. We can as well consider a relaxed spring mass system to analyze this first order approximated vibration, longitudinal vibrations. Actually, we have discussed the very same equations for the longitudinal waves on a relaxed spring mass system in a fair bit of detail in the previous video titled Lokayata and Shudra Physics. Please check that video for finding more steps of the math calculations that are skipped here. And also the video before that, Oscillations Beyond Newton. So you can check these videos. We will directly skip to the solutions of these force balance equations in this presentation. So using this force approximation, so this is for the y-axis, Fiy. So the yth component of the ith spring, force of the ith spring, the y component of it. So we get the y acceleration of the ith mass as this. So because of the sine function, we have got this extra yi minus 1 divided by L factor. And we know within this bracket, xi minus 1, which is much smaller than h. So to a first order approximation, the most significant leftover term in this equation is the kh factor. So kh into this difference in y, kh yi minus yi, this factor. So this is the leftover, because the other term is of higher order. It's an insignificant term. So in the longitudinal case, the kh factor had got cancelled, but in this transverse wave cases, the kh factor is the main factor. Here also there are force components from the ith spring and the I plus 1 spring. When we expand these terms, we get, so these terms, we saw this. So for a generic mass n, the equation we get is m d square yn by dt square plus kh by l into yn minus 1 minus kh by l whole into y of n plus 1 minus yn. So this should be nearly equal to 0, approximately 0, up to first order approximation. So note this depends on the pre-stretched factor h. So the modified or the effective spring constant in this equation in this case is kh by l. So in the longitudinal case, we just saw k in these places. With these differences, the disturbance differences. Here it is kh by l. So in the longitudinal cases, it was just k. Here it is kh by l. So if h equals 0, the effective spring constant in this equation becomes 0. So it is as good as that the spring is not there anymore. The transverse normal modes need the background tension in the spring for its existence. So in the first order approximation, the x and y axis vibrations have the same form equations. The mathematical form is same as the equations for longitudinal oscillations on a relaxed, non-stretched, non-compressed spring mass system. We covered that in the last video, Lokayata and Shudra Physics, on our YouTube channel. The only difference between the longitudinal and the transverse oscillations are this spring constant factor. That is spring constant factor. So in the longitudinal case, it is the actual spring constant k of the original springs. There is no change. So the original springs had spring constant k. Here also in the longitudinal case, when we frame this force balance equation, it appears as k. But in the transverse case, there is a modified spring constant, or a new factor which can be called as the effective spring constant, kh by l. So when h is 0, that is when the springs are not pre-stretched or pre-compressed, there can be no transverse oscillations up to this first order approximation. So as usual, to solve this, we can assume each disturbance has an SHM form solution, xi equals ci into cos omega d. So xi is the disturbance of each mass, ci is the amplitude of the disturbance, and omega is the frequency of disturbance. So it can be sine also. So we basically assume this SHM form, simple sinusoidal forms. So we can assume that the same SHM form holds good for the y disturbances. So instead of xi, we can have yi into ci prime cos omega prime t. So we can use the same forms, same mathematical form, keeping the amplitude and frequency symbols different. So instead of ci, we can have ci prime, and instead of omega, we can have omega prime. And further, we find these ratio between the amplitudes of the disturbances, these alpha values. And using this, and we get using these SHM forms and the alpha definitions, we get an exact form solution as this alpha, defined as the ratio of two sine functions. It is a very well defined function it is well defined at each mode r and at each mass I. So in case of closed chain, we get simple and exact analytical expressions. We already saw that alpha has this sinusoidal variation at each mode. These alphas are the amplitude ratios. So they determine the amplitude of oscillation at the different mass units. From this, we get the frequency at each modes as from this equation. So we put alpha 2 here and get this sinusoidal variation for the frequency. So note that this frequency has sinusoidal variation, it is not linear. Also, this frequency is framed in the radians per second units, not in the cycles per second. We may have to convert that later. So because the alpha variation is sinusoidal in the first step, we can clearly define a wavelength at each mode. And we get a simple expression for wavelength like this. So this is an harmonic series depending on the mode number r, and it goes as 1 by r. Like we defined a wavelength artificially, that is, wavelength is not part of the equations of motion in any way. So this does not appear in the equations as such. To begin with, it does not appear, and formally it is not necessary also in any way to describe the motion of the individual masses in the chain. It is not necessary. This factor, wavelength, this whatever we define this variable, it is not necessary to explain the motion of the individual masses. So it is just an emergent pattern that we recognize easily, that our brains recognize easily. So like wavelength, based on it, we can also define another variable called velocity. Depending on both this frequency and this artificial wavelength. So in fact, we define the velocity as multiplication of wavelength and frequency in cycles per second. So like wavelength, even this velocity is an imaginary construct, because in a normal mode, the shape is stationary. The net energy at each mass unit is conserved and not exchanged with the neighboring mass unit. So basically, in the normal mode, whatever we say, it is a stationary wave. It is not exchanging energy with its neighboring masses or anything. So this velocity is actually a misnomer, because there is no propagation as such. No energy is being propagated. So this velocity is not carrying anything really. So it is just an imaginary construct that we have created. So these oscillations cannot actually explain the energy propagation. However, we are more interested in the value of this velocity. Just note that this velocity is not a constant. At different modes, that is at different r values, it has different velocities. This is because the frequency does not scale linearly, and because the frequency is a sinusoidal function, we get this. If it was a linear function, we wouldn't have got this. So it has a velocity dispersion. The velocity has a dispersion when we consider this system as a spring mass chain with discrete oscillators. So from the ab initio first principle calculations using the force balance equations on individual mass units, we get these limits for frequency, wavelength, and wave speed. In the n mass n+1 spring, the lowest frequency is at the first normal mode. We get that as pi by n+1 into square root of k by m. So when n is very large, when n tends to infinity, the lowest frequency tends to become 0, because it goes as 1 by n+1. And the highest frequency tends to the limit 2 minus pi square by n+1 square whole into square root of k by m. So at very large n, when n tends to infinity, the largest possible frequency has a finite upper limit, 2 into square root of k by m. The longest wavelength is at the first normal mode. It is equal to this 2 into n+1 L. So this is nothing but twice the total length of the whole spring mass arrangement. So there are n+1 springs with length L each. So the total length of this arrangement is n+1 into L. But this length is 2 into n+1 L. So it is twice the length of the total arrangement. That is, in the first mode with the lowest frequency, we find half a wave from one crest to a trough along the chain. So we just find this half a wave on this chain. As the length of the chain increases, the longest possible wavelength also increases accordingly. The shortest wavelength is at the last normal mode, nth normal mode, and it is equal to 2 into n+1 L divided by L. So we can see as n tends to infinity, it has a lower limit, 2L. that is the shortest wavelength allowed on this chain, cannot be shorter than the length of the two springs forming the chain. So length of one spring is L. So the minimum possible wavelength is 2L. Any other wavelength should be higher than 2L. By multiplying the first normal mode frequency and wavelength, we get the first normal mode wave speed as L into square root of k by m. And in the limit where n tends to infinity, we get the last normal mode speed as 2 by pi L into square root of k by m. So numerically 2 by pi is nearly 0.63662. So it's here. So in the Newtonian method, we expect a constant speed L into square root of k by m, which is actually the speed at the first normal mode. So in the first few lower normal modes, we get a speed nearly equal to constant L into square root of k by m. It is in that limit, in the lowest mode limit, in the first normal mode limit, whatever the speed we get from the Newtonian method is the same as the first normal mode speed. So at higher modes, Newton's method, or which is equivalent to D'Alembert's wave equation. So Newton's wave equation or the D'Alembert wave equation have constant wave speed. And this constant wave speed implies an overestimation error of over 57% at the higher modes. Because instead of 0.63662 that we expect, that happens in reality, the Newton's equation gives 1. So 0.63662 to 1 has an error of 57%. And the most important bit about this exercise is not that this accuracy is bad. It is that we should recognize that both this wavelength and the wave speed are imaginary constructs. Probably the wavelength idea was created by Pythagoras or someone before him, because it is prominently visible on a string. It is very visual. When we excite a string, we see these kinds of shapes. So it is very prominent, and so it was defined, and then it was associated with energy propagation. But technically it can only be associated with stationary waves which are not carrying any energy, which are not involved in any energy transfers. So we basically get the idea of this constant wave velocity from Newtonian analysis of wave speed on a stretched string. In the books, this idea, this wave speed, constant wave speed idea is combined with the pre-Pythagorean concepts of modes. But we see that the calculations from first principles based on this Newton's own force balance equations contradicts this textbook picture of this combined Newtonian Pythagorean picture of the wave that we get is different from what we get from the Newtonian force balance equations. So in a sense, Newton's own equations contradict his own analysis. So the Newton's analysis of waves on a stretched string is not consistent with the ab-initio force balance method. Newton's speed can be an overestimate in excess of 57% at higher frequencies. So in such a case, using this equation to claim constancy of speed of light is highly dubious. Basically, Maxwell used this equation. This is the main theoretical equation that is used to derive the constancy of the speed of light. If this equation itself is wrong, if we cannot use this equation, this wave equation, then how can we claim the constancy of speed of light? Even that could be having a variable speed like this, like how we derived using these discrete oscillators. So in the transverse oscillations case, we get the same solutions, but the k is replaced by kh by L as expected. So this is the speed limits we get. Note this extra factor h by l in these terms. So in the longitudinal case, it will be just k by m inside the square root. Here in the transverse case, it is k by m into h by l. So we can define this term k into h as the background tension in the spring. This tension is due to the pre-stretched length h. So in the Newton's wave equation, we expect the constant velocity given by v equals L into square root of kh by ml. So this kh can be replaced by tension, and this L goes inside, it becomes T by m by L. So basically, essentially, we can write this velocity as square root of the spring tension divided by the mass per unit length. So this is basically what Newton derived. So because of this factor h by L, the transverse wave speeds will be much lower than the longitudinal waves. So because longitudinal waves just have k by m, and this has this extra factor kh by ml. Since h by l, h is much smaller than l, this transverse wave speeds will be much lower than the longitudinal waves for the same chain. On the same chain, if we excite the longitudinal waves and the transverse waves, we should get the transverse wave speeds to be much lower. The wavelengths between these transverse and the longitudinal cases will not change. They remain the same. The wavelength values do not change. But the transverse oscillation frequencies are again very small compared to the corresponding mode frequency in longitudinal oscillation. Both the velocity and frequencies are low in the transverse oscillation case compared to the longitudinal case because of this extra factor h by l. In the textbook description of waves, rather we should call it normal modes, not waves. In the textbook description of normal modes on a stretched string, which is consistent with the constant speed ideas of Newton and D'Alembert wave equation, and which is derived ignoring the individual oscillating units, discrete units within the string. In this case, in the textbook case, we implicitly assume that there are an infinite number of modes and there are an infinite number of links in the chain. So that is what is assumed implicitly. Usually the finite n in these expressions, which we found from the ab-initio force balance method, this n is usually ignored. This is actually a finite n. This finite n is usually ignored and it is assumed to be equal to infinity. What we know about the stretched string externally is its total length d. That is, we have n plus 1 into L equals d. But usually we do not know the individual values of n and L. Only thing we know is that n is very large and L is very small, but that may not be sufficient data. So this, coupled with the idea of constant wave speed, implies that the last normal mode or the infinite normal mode is technically having zero wavelength and infinite frequency, but with a finite velocity. Because when we ignore this 2 into n plus 1 term in the lower limit of the wavelength in the ab initio, in the above calculations, so we ignore that. We ignore 2n plus 1 here in the above. We basically replace this 2n plus 1 L by this total length 2D. Where n plus 1 into L is D, the total length of the arrangement. So 2n plus 1 L we just replace by some finite value D. We forget that there is a factor n inside that, and we think that it is a finite value. So we forget that. We ignore this 2n plus 1 which appears in this ab initio calculation. And the n in the below expression 2d by n, we use infinity in the place of n. So we use d in place of 2n plus 1l, and we carry forward the n, and unmindful of the fact that this n and the top n are the same, we just put n as infinity below. So in effect, it creates that the wavelength does not have any lower limit, it becomes practically zero. So basically this n in the denominator of 2d by n can far exceed the actual finite value of n that is there. So this is a wrong way of putting it. So we can basically put infinity here and we get 2d by infinity is 0. Similarly, the lowest mode frequency is given by pi into v by d. V we know it is the constant velocity factor, d we know which is the length of the total length of the string, pi is a constant, so we can know this. So pi v by d is the lowest frequency value, and the last mode, therefore the last mode will have n into pi into v by d. So n we replace by infinity, so it becomes practically infinity pi v by d, which is infinity. So this basically means that there is an infinite percent error at the highest frequency modes. In fact, basically putting this infinity here is an abuse of the concept of infinity. We have to be mindful of that there is this another n on top, 2n plus 1 by n. So n plus 1 by n, when n tends to infinity, it becomes just 1. And 1 by n as n tends to infinity becomes 0. So that is the difference here. So we should be careful of using the expressions on top, especially at the higher modes, higher normal modes. Otherwise we get the wrong wavelength limits and the wrong frequency limits. So in the textbook description of normal modes, so this is the problem we have, that we assume that there are infinite modes. So basically Newton's wave equation or the D'Alembert's wave equation, they wrongly get that the constant that there is a constant wave velocity on a stretched string. But in reality, the ab-initio force balance equations show a velocity dispersion, with the velocity varying between L into square root of k by m at the first normal mode to 2 by pi into L into square root of k by m at the last normal mode. The Newton's wave equation is true only at the very low frequencies when there are a large number of spring mass units in the system. In the textbook description, the non-zero lower limit in the wavelength is not resolved properly, since there is an implicit assumption of infinite modes. So basically there is a lower limit 2L. Newton's method or the textbook description does not resolve it, and therefore in the textbook method the wavelength can become 0 and the frequency can become infinite. In the actual ab initio normal mode calculations, we get a finite non-zero limit on the wavelength. The lower limit is equal to twice the size of the individual springs making the chain. That is, the minimum wavelength tends to be 2L as n tends to infinity. As the number of chain, even if the number of spring mass units tends to infinity, this lower limit does not change, it remains 2L. But in the textbook method, there is no lower limit on wavelength. It can be practically 0, and there is no upper limit on the frequency. The frequency can be practically infinite. So this is the discrepancy between the Newton's method based on the wrong ideas of waves, and this is the Newton's method, Newton's own force balance equation method. So this is the Newton's wave method, and this is the force balance method using Newton's own force balance equations. Most importantly, among these three variables, the speed and the frequency and the wavelength, only the frequency is the real variable which appears in the equations of motion. The wavelength shape and the wave speed derived using the shape of the amplitude variation are imaginary constructs which are not necessary to describe the motion. This velocity is not even associated with any energy propagation. because the normal modes describe a collection of localized oscillations, localized energy, stationary waves. So we have discussed about the energy propagation, what are the kinds of things we need to do, describe the energy propagation in 1-2 previous videos. Basically, we need non-normal modes to understand those propagation. You can watch those videos. We end this presentation here. Thank you.